Welcome back to the Physics Bible. In this video we're going to look at paper 6. And remember, you can do this. Okay. The first chapter is about energy, force and work. Let's get straight into it. This first question. A worker pushes a box up a ramp for 5 meters. How much work is done on the box? The equation for work is work equals force times distance. Now I've circled the two numbers that we need to complete the question. We have the force that's been applied to the box and we have the distance. It's important to note that the force that's being applied to the box must be in the direction that it's being pushed, or that the distance is being measured in. So the 5 meters up the ramp actually means 5 meters that way. Even though the height will only be 2 meters, the box will actually be pushed 5 meters in the direction of the force, and that's the important thing. So you'll see that the work done is 150 newtons multiplied by 5 meters, 750, and the unit is joules. Had a bit of a mare there at the start. Obviously, the unit for work is the same as the unit of energy, which is joules, obviously not newtons. If the box weighs 100 newtons, how much work is done if a crane is used to lift it straight up by 2 meters? I'm going to highlight the numbers that we've got. In this question, a box is simply being lifted straight into the air. If it's got a weight of 100 newtons and it is lifted straight up, then all we have to do is multiply the force, which is the weight, by the distance that it's lifted straight up, which is 2 meters. So in this case, the work done is force times distance, 200 joules. The next question, how much work did the worker do against friction? Explain your answer. So again, reminding you what you should do is pause the video, have a think about that question. You're going to have to refer back to these answers. I'll give you a second and then we'll resume. Okay, so the worker did 750 joules of work to get it from the bottom of the ramp to the top of the ramp. But if we just lifted it straight up, the actual gain in energy of the box is 200 joules. A box of that weight, lifted to that height, would gain 200 joules of gravitational potential energy. But the worker had to do 750 joules. So our answer for this is 750 joules minus the 200, as the difference is the amount of joules that was lost to the surroundings, that was dissipated. So we can say that 550 joules, this was work against friction, and we can say that the energy was dissipated to the surroundings. That'll be in the form of sound energy, heat energy on the floor as it's scraping along. If it takes the man 1 minute to push it up the ramp, what's his power? This is another calculation question. The power equation is power is energy divided by time. Let's highlight what we've got. So what energy value are we going to use? It has to be the energy that the man actually spent. This is how much work he did on the box. 200 of it went into lifting it up, but 550 went into wasted energy. So the total energy that he used was 750 joules, and it took him 1 minute. The mistake most people make here is that they would just put 1 and give a power of 750. But time needs to be in seconds if we're to get a unit of watts for power. So 750 divided by 60 gives an answer of 12.5, and the unit for power is watts. That means that the man transferred 12.5 joules per second, and he did that for 60 seconds, which means a total of 750 joules was transferred to the box. If the crane has a power of 50 watts, how long will it take the crane to lift the box? So if a crane comes in and lifts the box straight up, it's going to lift it 2 meters. We know that there's 50 watts of power on the crane. And the question is how long? So have a think what we're being asked to work out, and then we'll resume in a second. Okay, because it's asking how long, what we're actually wanting to know is what's the time period? How long will it take? How many seconds will it take for the crane to lift the box? We've been told the power is 50 watts. Well, what equation do we know with power and time? It's this one. We've got the power. I've got the power. And we've also got the amount of energy that the crane does. If the crane lifts it straight up, then it's actually doing, we've worked out that it's doing 200 joules of work. To lift a box directly up would take 200 joules. So the crane does 200 joules of energy is transferred. We don't know the time. Instead of writing P, because we've got it, we can write 50. And then it comes down to rearranging the equation. So we want T equals. Hopefully we're comfortable with doing this now. Rearranging the equation, we're going to bring the T up and the P is going to go underneath. So it's E divided by P, 200 divided by 50, and so we get a final answer of 4 seconds. Next question. Name 3 contact forces, and the question after that is name 3 non-contact forces. Write down your answers and then check back in a second. Okay, so 3 examples of contact force are friction, upthrust and drag. The normal contact force is also a contact force, which is the force that is pushing back on something as you push against it. We'll come to that in a second. 3 non-contact forces: magnetism, gravity and the electrostatic force. So just so we're happy with these going forwards, friction is to do with anything where 2 or more objects are rubbing together. Upthrust can only be attributed to forces acting up in water. So upthrust sometimes gets confused with the normal contact force, this force acting up. We'll make sure to write water just so that we remember that. Drag is any sort of resistive force. It could be air resistance or water resistance. The non-contact forces, magnetism, the force between anything magnetic that is in a magnetic field. Gravity, the force between two objects that have mass. And the electrostatic force is the force between two or more charged objects, things that are positive and negative. Explain what a normal contact force is, and give an example. So the normal contact force is one of the most common forces that you come across on a daily basis, because it is simply the force that's created whenever anything pushes against something else. An example could be the physics Bible just sitting on this desk. The physics Bible is pushing down on the desk, and the normal contact force is the desk pushing up on the physics Bible. So if we have a table and we have the Bible, of course, let's make the Bible red. The weight of the book is the first force that we're going to draw on the diagram. W, it acts straight down, so the weight of the book is pushing down on the desk. And I'm going to write an N for normal. Sometimes we write R for reaction force, but that's the force pushing up on the book. And that's why the book stays still. The resultant force of these two forces is 0. With no resultant force, it means there's no acceleration, the book stays still. Draw an arrow on the diagram to show the force of the Earth on the Moon. Label it EOM, Earth on Moon. Draw an arrow for the force of the Moon on the Earth. Label it Moon on Earth, MOE. So we've got the Earth and we've got the Moon. Read back over those questions, make sure that you draw your arrows the correct size and in the correct direction. Let's see if you get it right. Pause the video, have a go, and then check in a second. Okay. The force of the Earth on the Moon, the Earth is pulling the Moon in that direction, towards the middle of the Earth. So I'm going to label that EOM. And the next one, MOE, is the Moon on the Earth. Well, I'll change to green to show this arrow, and it's going to be an arrow which is exactly the same size, but in the opposite direction. This is an example of an action-reaction pair. An action-reaction pair acts on two objects. We've got two objects and the forces are acting on the separate objects. The Earth pulls the Moon, therefore the Moon pulls the Earth. This is also an example of a non-contact force because the objects aren't touching. The normal force is the force that we draw on the one object, in this case the physics Bible. Both of these forces are acting on the physics Bible, and this is a contact force, an example of a contact force. What do you call a pair of forces that are equal and opposite but acting on different objects? Now I've just covered this. Can you remember? That's an action-reaction pair. Give another example of the above type of interaction. Well, we've already given one, the Earth pulling on the Moon. Rather than gravity, can we think of another one? What do you reckon? I think the easiest one here would be two magnets pulling towards each other. So the south magnet, which we'll make blue, just to make it clearer, and the north will make red. So which way will the blue arrow be and which way will the red arrow be? Have a think about it and add it to your diagram. Okay, so the south pulls the north to the right, and the north pulls the south to the left. They have to be the same size but in opposite directions. So this action-reaction pair is a bit like the Earth and the Moon, non-contact as well. Magnetisms are non-contact. And going back, the normal contact force, again, look, it's acting on one object, whilst here the forces are acting on separate objects. So what's going to happen to the South Pole? Well, there's a force acting to the left, so the magnet's going to accelerate to the left. What's going to happen to the North Pole? Well, there's a force acting to the right, so the north is going to accelerate to the right, and they'll end up meeting somewhere in the middle. For the reaction force, or the normal contact force, those two forces are acting on one object, and the resultant force in this case is 0, so there'll be no acceleration. The book will stay where it is. Next, complete the free body force diagram below so that the resultant force is 0. So we've got a trolley, we've got the weight of the trolley, the thrust acting on the trolley. I want you to add as many or as little arrows as you want. Be careful with the direction and be careful with the size. We want the resultant force to be 0. Once you've done that, I'd like you to suggest some names for the forces that you've added. So what would be typical names of forces that would realistically be acting on a trolley and cause the resultant force on the trolley to be 0? Okay, so we're only thinking about the trolley. If there's a weight force acting down, this must mean that the trolley is falling down or accelerating towards the centre of the Earth. But it doesn't. It's not accelerating, and that's because there must be another force that's equal and opposite. It has to be the same size, so that the resultant force is 0 in the vertical direction, but in the opposite direction, so that they cancel out. This is the normal contact force. The floor is pushing up on the trolley. Now it doesn't matter if I add it at the floor, but I'm just going to put it there so that we can see those two are opposite and equal in size. What about thrust? Well, there must be a force acting in the opposite direction, and we'll make sure that's the same size as well. What could that be caused by? Any sort of drag or friction. So there's force forwards and a force backwards, same size opposite directions, they cancel out. There's a force down, but the floor's pushing up on it, they cancel out. Now, even though the resultant force is 0, is this trolley moving? And how can you tell? It is moving. It must be moving because there's a frictional force acting against the trolley. So in this case, even though the resultant force is 0, it just means that the trolley is travelling at a constant speed. State one action-reaction pair of forces in the example. Hint, action-reaction pairs need two objects. So in the example that we've just done, we saw an example of an action-reaction pair. The trolley pushes down on the floor pushes up on the trolley. But an action-reaction pair is more like the magnets, or the Earth pulling the Moon. Have a think about what other force must be coupled with each force in this diagram. Okay, well let's start with weight first. Weight is the earth pulls the trolley down. The earth pulls the trolley down, so the trolley has a weight. The reaction to this is that the trolley pulls up on the earth. And believe it or not, it pulls up on the earth with exactly the same size force. The difference is, because the earth is so big, that pull up on the earth essentially has zero effect. But the force is there. What other forces have we got? Thrust. What is thrust? Well, it's a force pushing the trolley forwards. Why is the trolley being pushed forwards? If there's an engine in the trolley, it wouldn't be a trolley, it would be a car. Let's say there's an engine in this trolley, and it causes the wheels to turn. The wheels push back on the road. And you can see this when, I don't know if you've ever watched rally, you'll see with a rally car and on loose gravel, the stones get thrown backwards. So the wheels are trying to push the road backwards. If the road isn't solid and it's loose like gravel or dust, then actually the wheels will throw that debris backwards. The reaction to this action is that the road pushes the wheels forward, and that's why the trolley goes forwards. So there's two examples. The normal contact force, you could have said that the trolley pushes down on the ground pushes up on the trolley. They're the two objects there, the trolley and the ground. And finally friction. Friction is acting back on the wheels or on the trolley, so you could say the trolley pushes the road forwards, or it's trying to push the road forwards, and therefore the reaction is that the road is pushing back against the wheels. Or you could say the trolley is pushing the air forwards, so as it moves forwards it's bumping into air particles, and the particles are pushing back on the trolley, and that would be the case of, if we'd said air resistance. What term do we use for two objects that are pulled together due to action-reaction pairs? So what term do we use for two objects that are pulled together due to action-reaction pairs? So we call this an attraction. An example, well, we've got an example over here. Gravity is always an attractive force. What term would we use for two objects that push apart? What would the answer to that be? Well, if the two objects push apart, we would use the word repel or repulsion. Examples of that are if you had two positively charged objects, they push away from each other. You're probably familiar with if you bring two magnets close to each other, a north and a north or a south and a south, you get repulsion. So the next part, we're going to look at vector diagrams, and for that we're going to need some graph paper. On this graph paper we've got two force vectors. They have a size and a direction. The first one is 12 centimeters long, and we're going to say it's 120 newtons in size. And this one is 7 centimeters long and it's 70 newtons in size. This means that we've got a scale, and in the exam you might have to come up with the scale yourself, or the exam might give you the scale, and so you would have to draw, you maybe even would have to draw the first two vectors. Once it's set up and you followed the scale, and I'm going to make a note of the scale, so this means that 1 centimeter equals 10 newtons. So 12 centimeters, 120 newtons. To find the resultant force, we're going to do what's called the parallelogram method. We're going to make a parallelogram. A parallelogram is a shape which has got two lines which are parallel to each other on both sides. So we need a line which is parallel to that one, and that's going to go there. And then we're going to use a line that's parallel to that one, and that's going to go up the top. Now, you've got to make sure that in the exam you leave enough room to complete your parallelogram. By the magic of technology, I'm going to be able to rectify this pretty quickly. But just so you know, the reason why I know I've done a mistake is because the size of that arrow, 7 centimeters, it needs to be 7 centimeters up there. And due to a miscalculation, you can see that I've actually only got 5.5 centimeters. Just give me a sec. And just like that, we've got a new diagram. I've obviously kept the direction of the forces the same, but we've changed the scale. 1 centimetre is 1 newton. Just to keep it simple, we've got 10 newtons and 7 newtons. That side is 10 centimetres long, and that side is 7 centimetres long. Now we can do the parallelogram method. Let's draw the 7 newton one first, because it's often a lot easier to do a vertical one or a horizontal one if you've got it, because we can follow the lines. Now I'll use black just so that we can see that these are the forces that we've moved. So that's 7 newtons. So that gets tagged on to the end of that 10 newton arrow, and now we have to tag the 10 newton arrow onto the end of the 7 newton. But because I know I've done that right, I don't even have to try and get the angle right, because I know that it should match up from corner to corner, and that it should be 10 centimeters long, and you can see it is. Now that we've drawn the parallelogram, the last thing that we've got to do is draw a line from where we started to where we finished. And the forces here were to the left and up and to the left, so no surprise that our resultant force is up and to the left. And the size of it, we'll go right from that point to that point, is 15.8. 15.8 centimeters, which means, because the scale is 1 centimeter to 1 newton, the resultant force is 15.8 newtons. So a 10 newton and a 7 newton force combined together at these angles would give a force of 15.8 newtons at that angle, which we'll just call A. You could measure it with a protractor and actually say what direction the resultant force is. Now I should mention that this question and the one that we've just done, they are only a higher tier question. So if you're doing the standard tier exam, you won't have to do these. If so, just click ahead until you see the next question. For now, we're going to look at how to what's called resolve this force into its components. Now the word resolve means kind of to work out, and components means the bits that make it up. So we're going to work out the bits that make up this force in the vertical and horizontal. Now in our last question we were given a horizontal and a vertical, and we could put them together and we could get the resultant force from it, like that. This time we've actually got the resultant force, and we need to work out these two bits. To do that, we need to complete the triangle. So I'm going to put a mark on the graph where we are, which is there and there. Draw a line down, and then a line along. And that means that to make that 300 Newton resultant force, we would need a force down and to the left, because the resultant force is down and to the left. Now it says it's 300 newtons, and if I measure that, you can see that that's 15 centimetres long. That means that 1 centimetre must equal, well, if it was 10 newtons, then it would be 150, so it actually has to be 20 newtons. So for every centimetre, we've got a scale that gives us 20 newtons. So how many newtons is this force? You'd measure it, and I can tell you that that is 11 centimetres, and the horizontal is 10 centimetres. So the question could ask, resolve this resultant force and state the size of the vertical component in newtons. Well, 11 centimetres, 20 newtons, so the force of this vector here is 11 times 20, which is 220 newtons. This one, 200 newtons. So a 220 newton force down, added to a 200 newton force to the left, will give a resultant force of 300 newtons in that direction. That brings us to the end of CP7 and 8, which is forces, energy and work. Next up, it's electricity. See you in the next video.